Now, let me start with the actual mathematics. And before we talk about characteristic classes, and here today I will even not tell you what characteristic classes are, we'll come to that later. Let me give you a few sample questions which can be attacked with this kind of thing. So characteristic classes are in a way a tool which allows us to answer certain geometric and topological questions. So let's start with a few such questions. So the first thing is, and I have it already mentioned on the web page, is the hairy-ball theorem. That's a very classical theorem. In German it's called Igelkerrungssatz. And what does it say? Well, it says this, any, let's say, smooth vector field on the two-sphere, this is why it's the ball, any smooth vector field on the two-sphere has zeros. Or at least 1 0, I should say. So do not exist any smooth vector fields on the two-sphere without zeros. And you can think of the sphere equipped with the vector field as a hairy ball, and the hairs are tangential to the ball. And if this is done in a smooth manner, or you could even replace smooth by continuous, makes no difference really. If these hairs are combed in a continuous manner, at some point there must be a zero. And in fact, so you have probably seen this before, in fact this doesn't only hold on S2, we could also use other surfaces here, more generally. Any compact, connected, oriented surface with Euler number not equal to 0. So S2 has Euler number 2, and a pretzel surface has Euler number -2, and there's only one such surface which has Euler number 0, which is this. Which one is excluded by this condition? Say again, I didn't hear it.
Torus.
The torus, okay. And the torus is excluded, and it's excluded for good reason. So for the torus, E2, the theorem is false. Or the conclusion of the theorem, I should say, is false. Conclusion does not hold. So we really need this assumption. Namely, you can easily draw such a vector field. If you look at the torus, and then you foliate it by these circles, right? So the torus is S1 cross S1. So you have all these S1s, and then you can look at the velocity field of each of these circles. This would give you, going around, so this would give you a smooth vector field with no zeros, so it doesn't vanish anywhere. And so now the question is, so what we have here somehow is a statement of the sort, we have some topological condition on the manifold. From this, we conclude something about existence of certain vector fields. Vector fields are sections of a certain vector bundle, namely the tangent bundle. And so we conclude something about the tangent bundle. So it's a statement of the form, a certain topological condition or geometric condition of the manifold has consequences for certain vector bundles over that manifold. And this is exactly the kind of questions which one can deal with using characteristic classes. So the question is, of course, why is this true? And we will see why this is true. So that's sample question number 1. Second question. division algebras. Something seemingly totally unrelated. So what's a division algebra? Definition: an algebra A over some field need not be commutative, need not even be associative. So not necessarily commutative or associative. An algebra is called a division algebra. If we can divide, meaning if for any two elements in our algebra, A and B, B non-zero, there exists unique elements X and Y, such that, well, A is equal to X times B. So we can solve this equation uniquely for X, and A is equal to B times Y. We can also solve this equation. Since it's not commutative in general, X and Y will not be the same. And but nevertheless, so what we can do somehow is we can divide A by B from the left and from the right. So that's a division algebra. And now the theorem is, due to Stiefel, the dimension of any, so let's look at division algebras over the reals, so over any real, and in order to talk about the dimension, it should be finite dimensional, of any real finite dimensional algebra is a power of 2. So what are examples of division algebra? So let's say real and finite dimensional. Do we know? Who gives me an example? How about R itself? With the usual multiplication. Certainly works, right? So it's a one-dimensional real division algebra. What else? You know the second example, at least from the first semester. Yes, exactly. The complex numbers form a two-dimensional real vector space. It's an algebra with complex multiplication. And in this case, there's no difference between X and Y because it's commutative. But we can uniquely divide, right? Anything else? Quaternions. So that's a four-dimensional space over the reals. It's again a power of 2, right? Looks good. Yes, quaternions is not commutative, right? But it is associative still. An example which is neither commutative nor associative. Now it became easy, right? Now that we saw the pattern, the octonions, yes, that's 8. Again, it's a power of 2. So the theorem in particular says that you should not look for such a structure on R3, for example, right? You might naively think there could be something between the complex and the numbers and the quaternions. No way, there is no such thing. In fact, the stronger thing is true, namely that these are actually all examples. So that's stronger than the Stiefel theorem. We won't be able to do that in this course, but at least we will be able to prove Stiefel's theorem. And now you may wonder why such an entirely algebraic statement has anything to do with our course. And the reason is that if you have such a division algebra, you can derive geometric information from it, to which you can then apply the theory of characteristic classes, and we will see how that works. Okay, so that's the second example problem that we will be able to, that we will deal with. Third example. Now, if we look at complex projective spaces, CP1, for example. So what is CP1 actually? It's a fancy name for something very simple. Normally, CP1 is known under a different name. Complex projective space, one-dimensional space, one-dimensional in complex one dimensions. Actually, it's already on the blackboard. It's a compact manifold, actually. So it cannot be. Yeah, it's S2. As a manifold, it's the same thing as S2. Yeah, it's also known as the extended complex plane when you add one point at infinity to the complex plane. Anyway, so this is as a manifold, this is the same thing as S2, and this certainly embeds into R3. So this sits as a surface in R3. And R3 certainly sits in R4, which is C2. So in other words, it's possible to embed CP1 in C2. Okay. Now, the question is there an embedding of CP2 in C3? So CP2 is a two-dimensional complex manifold. So it's a four-dimensional real manifold. And C3 is the same as R6. So the question is, can this four-dimensional thing be embedded in R6? And now, how can one answer the question? If the answer is yes, you can answer it by finding such an embedding, writing it down. If the answer is no, what do we do? If the answer is no, we will not find a solution or an example or such an embedding, but this doesn't, that we don't find it doesn't mean it doesn't exist. And the theory of characteristic classes will tell you that this is not possible. No. Okay, so you see these characteristic classes, whatever they are, can be applied in many contexts, and if you do mathematics in various fields of mostly pure mathematics, then they will always cross your way. So it's really good to understand what's going on here. Any questions so far? Not for now, right? Good. Okay. So now let's start with the actual course. And in fact, I will start with some preliminaries. And also, I guess, the prerequisites are different from participant to participant. So we start with some basics. Oh, before I start, I should make another remark. The theory of characteristic classes can be approached from different directions. There's a more topological approach and a more geometric approach, or differential geometric approach. This is mostly due to the fact that one can use different theories of cohomology. Topologists like to use singular cohomology, whatever that is, and the differential geometers like to use the round cohomology, which is based on differential form, which is something differential geometers like. And these approaches are not entirely equivalent. They have a huge overlap, but they are not completely equivalent. So the advantage of the topological approach is twofold. The cohomology theories that the topologists use are a bit more refined. So sometimes the characteristic classes that occur carry a little bit more of information. For those of you who know what I'm talking about, this refers to the fact that integral cohomology can have torsion, which one loses when one passes to the round cohomology. However, this refinement is in most examples not relevant. There's another advantage of the topological approach, which is that you can apply it not just to manifolds, but to more general topological spaces. So that's certainly an advantage. However, for these things that I've mentioned and for most applications, this doesn't make a difference. And the third thing is that some types of characteristic classes can take their values not in real cohomology, but in, for example, Z2 valued cohomology. Stiefel-Whitney classes are an example of that. And these cannot be treated well using differential forms. So some of the classes are not really approachable well through the differential geometric approach. However, the differential geometric approach has certain advantages. For example, big advantage is that so-called secondary classes are treated much more easily. If there is time in the end, we will discuss that too. You may have heard about Chern-Simons forms and that sort of thing. So this is what comes up in this context. It's also important in mathematical physics, actually. And also some of the constructions are simpler and more intuitive. For example, there's a thing in algebraic topology which is called the Gaussian sequence, which is complicated to construct. You need spectral sequences and all kinds of algebraic machinery. And in differential geometry, this is just fiber integration. You take a form and you do integration, you partly integrate it away. So that's a very simple procedure. So some of the things are more natural and more visual in some sense in the geometric approach. And of course, this is a differential geometry 2 course, so it's clear which approach I'm taking here, right? So we will use this geometric approach. But I want to mention it anyway because in the literature you find both, and so that you shouldn't be surprised if you see other approaches. Okay, but now let's start with the preliminaries. And the first thing is a very quick reminder of manifolds. I assume so that everybody here knows what manifolds are. Nevertheless, I want to say a few words about them because I will need one very useful statement, which is typically or is often not treated so, or not mentioned really. And this is the following thing. So let's first recall what a manifold is actually. So let's start with the topological manifold. So a topological definition, we'll start really at the very beginning. So a topological space N is called the topological, it's called an n-dimensional topological manifold if three conditions are good. First condition, and that's the important condition, is the space is locally homeomorphic to Rn. So N is locally homeomorphic to Rn. What does that mean? That means for any point M, there exists an open neighborhood of P, U and M open, containing P, and there exists an open subset in Rn, and a homeomorphism between U and V. There exists a homeomorphism, let me call it little x, from U to V. So for each point we can find an open neighborhood which is homeomorphic to an open set of Rn. So locally near every point the manifold looks exactly like Rn. That's the important property of an n-dimensional topological manifold. Now there are two additional assumptions which in many cases are not strictly necessary, but for some they are, and so we should mention them for completeness too. Namely, so locally homeomorphic to Rn, that's the important thing. M has to be Hausdorff. That's a separation statement. So that means for any 2 points, P P and Q in M not equal, we can find disjoint open neighborhoods. So there exist U1, U2 in M open, P in U1, Q in U2, and the two open sets do not intersect. So we can separate points by open subsets, by suitable small open subsets. That's the Hausdorff condition. And the third condition is that the topology of the space should not be too large, in the sense that it should have a countable basis for the topology. So there exists, so the topology of M has a countable basis. So that means countable basis. So that means we can find a countable set of open subsets. There exist countably many subsets, U1, U2, countably many in M open. So they are numbered, so they are countably many, such that each open set is a union of some of them. Each open U in M can be written as a union of these. Not all of them, some of them can be written, I write it explicitly, as U equals union Uij, where J, so for some of these, yeah, not all of them, of course, but some of them. They can be written in this form. So, for example, Rn has a countable basis. What would be a countable basis for the topology of Rn? Is this a question or an answer?
First, the question. I think at the second property we read that the intersection is empty.
Is empty. Sorry. Yes. Many thanks. Mm-hmm.
And for a countable basis, then we take the balls around points.
So balls, open balls of some radiuses and some centers, they form a basis, right? Every open set can be written as a union of open balls. But these are not countably many, right? So if you take all balls, then already the possible centers are uncountably many. So only rational centers and rational radiuses are sufficient to write any open subset, as you can write them as a union of such balls, and this gives you as a countable basis. Okay, great. So, but as I said, actually much of the theory, even in differential geometry, could be done only later with the first condition, and you could, for many cases, things you could actually drop condition 2 and 3, but for some things you need them, and this is why we'll keep them. All right, so that's a topological manifold, and you all know that, right? This is just a reminder. And what I want to now emphasize is that in some cases you are given a geometric object, some set of, we'll write down an example in a moment, and you want to turn this into a manifold. So you don't even have a topology yet, but you want to turn this into a manifold. And so let's see where this would apply. And so, for example, maybe I start with an example before I write down the theorem. let me come back to projective spaces, which I mentioned in the introduction. And so let's look at real projective space. So what is it actually? Real projective space, RPN, or very often it's also written as projective space of Rn plus 1. Note the shift in dimension here. So what is it? So that's a set of subsets of Rn plus 1. Namely, it's the set of all subsets L in Rn plus 1. So, and these L's are lines, or more precisely, they are one-dimensional subvector spaces. So L is a one-dimensional subvector space. So lines through the origin. And it's called projective space of Rn plus 1 because we are taking all lines in Rn plus 1. But it's written Rpn because this n refers to the dimension of this space. And as we will see. And now you see this is just a set, right? It's just a set. But I want to, I'm saying that this is a manifold, an n-dimensional manifold. And how do we now turn this into an n-dimensional manifold? So we have to construct a topology, right? We have to come up with a topology such that these conditions in the definition hold. And this is what the following theorem does. And that's actually the reason why I'm repeating this theory of manifolds. So here's the theorem. Let M and A be sets. So M is the thing that I want to turn into a manifold. So in the example, it's Rpn. And A is just an index set. Okay, and for any alpha in A, suppose we are given a subset of M. So we are given subsets U alpha in M and V alpha in Rn. Such that bijective maps X alpha from U alpha to V alpha. So far there is no reference to continuity or topology or anything. So suppose we are given that. So these will be the candidates for these local homeomorphisms that I have to find according to the definition. And these local homeomorphisms are called charts. Right? So these are the candidates for the charts. But so far there is no topology. So no, it doesn't make sense to talk about homeomorphisms. And now suppose the following holds. Suppose three conditions. First condition, the union of these U alphas cover the whole space M. So the union of the U alphas is all of M. Secondly, if we intersect two such U's, U alpha and U beta, and we apply the X alpha to it, then what we get is a subset of V alpha. And these subsets have to be open. So this is open in Rn for all alpha and beta in A. Well, that makes sense. In Rn we have a topology. And these are subsets of Rn. And so we require them to be open. In particular, this means that the V alpha is open. Because you could put alpha and beta equal, then you have the intersection will be just U alpha, and if you apply X alpha to it, you get V alpha. So V alpha is assumed to be open also. It's a special case with the second condition. And finally, if we take this set, and we could also take the set of the same intersection here, but apply x beta to it, then this is a subset of the alpha, this is a subset of the beta. And we can map one thing into the other because these x's are bijective. So we have a map going first apply x alpha inverse followed by x beta. So this is a bijective map from this set to that set. And now these are subsets of Rn. And as we know by the condition 2, they are actually open subsets of Rn. And the condition 3 is now that these maps between these subsets are homeomorphisms. That makes sense because we are talking about maps and subsets in Rn. And these are homeomorphisms. So this is homeomorphism for any alpha and beta in A. So that's the assumption. And then the conclusion is that there's a unique topology on M such that these U alphas are open and the X alphas are homeomorphisms, so that in particular that the first condition of the definition is satisfied. So then there exists a unique topology on M such that U alpha in M is open and X alpha from U alpha to V alpha is a homeomorphism for any alpha in A. So that's the conclusion. So this covers the first condition, the important condition in the definition of manifolds, and we will see add-ons, easy add-ons to this theorem that will then also guarantee the other two conditions. We'll come to this later. So that's a statement. And now we could try, before I say anything about the proof, we could try to apply this in the example. So we should be able to topologize this set of lines in such a way that at least the space is now locally homeomorphic to R, which would then in fact justify this index n. So let's see how we can do that. Okay, so if this is our M here, so that's now the M of the theorem. The question is, what's the A? So what are the candidates for maps, for charts in this example? And there are various ways to do it. Let me do it like this. So the set A I define in this example as the set of all affine linear embeddings alpha from Rn into Rn plus 1, which is where our lines live, such that 0 is not contained in the image. With 0 is not contained in the image of Rn. So this image is an affine hyperplane in Rn plus 1. So this has maximal rank because it's an embedding. So these alpha of Rn's is an affine hyperplane, but it's not, does never contain the origin, so it's not a vector subspace. So that's the thing. And to each such alpha, I somehow have to construct a map from a certain subset of lines, or certain set of lines, into Rn. Right? So how can we do that? So if we have such an affine linear embedding, how can we explicitly write it down? So for alpha in A, there exists a matrix B, a real matrix, n times n plus 1 matrix, with real coefficients. So that's a linear part, and it has maximal rank because it's an embedding. So of rank, the rank is n, maximal rank, and there exists a translation vector C in Rn plus 1, such that alpha of x is of the form b and x plus c. Right? This is how affine linear maps look like. And in fact, the c, so the c cannot be in the image in the image of this linear map, because otherwise the affine space would contain 0. All right, but anyway, so this is how these look, and so what is now the corresponding map x alpha, and what is the u alpha, and what is the v alpha? U alpha should be a subset of projective space, V alpha should be a subset of Rn, and X alpha should be mapped between them. So what is it? And so let me write it down. U alpha, I set to the set of all those lines, for which, if I look at this affine hyperplane, and so that's a hyperplane in Rn plus 1, L is a line in Rn plus 1, I can intersect the two, and I want to have that this intersection is not empty. So in other words, I'm excluding those lines which are parallel to this affine hyperplane, because those would be the ones which never hit this hyperplane. So that's U alpha. The V alpha is all of Rn, and the X alpha, mapping U alpha to V alpha, goes like this. So we take a line, and then we should get some point in V alpha. So what we do is we take this intersection, and this line and the hyperplane, actually, if they intersect, then they intersect in exactly one point. So that's a 1 point. And so it's 1 point on this hyperplane alpha of Rn. Now alpha is an embedding of Rn onto this, so it's a bijective from Rn onto its image. So we can take the pre-image, which is then an element in Rn. So the picture is this. So here's the origin. Then we have somehow this. This is our alpha of Rn, and now we have a line L. So that's our line L. So they intersect in exactly 1 point, and the alpha is a map from Rn onto its image bijectively. So that's the alpha. And so the line L is mapped. You take this intersection point and go back into Rn, and that's the image point. So that's the geometric construction. Okay, and so we need to ensure that this is bijective, but if you have two different lines, they intersect in two different points, and so they result in two different points here too. So it's obviously bijective. It's also, obviously injective. It's also surjective, because any point here corresponds to any point here, and then there's a line hitting intersecting there. So the inverse map is actually even easier to write down. So the inverse map, this takes an element in Rn, let me call it little v. What does it do? So it takes a little v, then we we have to apply this embedding alpha to it. Then we get the corresponding point in the affine hyperplane, and now we want to get to the line that intersects at this point, but that's exactly the line that is spanned by this vector. So it's the span of this vector. So that's the inverse map. All right, so yeah, now we have an index set A, all these embeddings. We have the U alphas, we have the V alphas, that's always Rn, all of Rn, and we have the bijective maps between them. And then in order to apply the theorem, we need to check these three conditions, right? So the first condition So as to the conditions in the theorem, so the first thing is, so we have to cover, or if we, all the U alphas cover all of M, and here I'm actually already proving a little bit more than that. Namely, I will select a finite number of U alphas which already cover everything. So that's a stronger statement that I'm proving here. Namely, so let's say alpha j, so for j from 1 to n plus 1, let's write down a corresponding such embedding, and it looks like this. So we have this vector in Rn, right? So alpha j must be an embedding from Rn into Rn plus 1. So that's a vector in Rn, and so what we do is we maybe I should say that, let's say E0 up to En, so that's the standard orthonormal basis of Rn plus 1. Well, that's the notation I want to use now. And so I should also number this from 0 to n here. And so the vector that corresponds to the j is just taken as it is. So that's my translation vector, c. And the others get just multiplied by the coefficients of v. So we have v0, let's now, this is from Rn, v1, v0, all the way up to vj, ej minus 1, plus ej, and then plus ej plus 1, ej plus 1, all the way up to vn plus 1, no, it's vn, en plus 1. So this ej plays the role of the translation vector c, and this is the linear part where we just multiply, and we have a shift in arguments when we get across this j's segment. That's true. Yeah. Right. Thanks. Good. So that's my affine linear map. And so what's the corresponding image? So if we draw the picture, so what's the image? Well, the image consists of all linear combination of these basis vectors except for ej. So in other words, the image is, so the linear part, the image of the linear part is the orthogonal complement of the vector ej. And then we shift it in the direction ej. So here's the ej direction, and let's say here are all the other directions spanned by E0, then we leave out ej and go all the way up to En, so that's all the orthogonal directions, so that's the orthogonal complement of ej. Maybe that's the origin, and then we shift this here, and that's now alpha j of Rn. Take the orthogonal complement of ej and shift it along ej to get a affine hyperplane. So, okay, so these are just particular examples of these affine linear maps here. And my claim is these things, these are already enough to cover the whole space. We don't need all of them, these are uncountably many, but these finitely many are already good enough. Do this here. So I claim that if I take the union of the alpha j from 0 to n, claim that this is already all of Rn. Well, let's say, let L be some element in here. And let's assume it's in none of these U alphas. So assume L is not in U alpha J, or any J from 0 to n. So what would that mean? So which are the ones that are left out here? If it's not, if the line is not in alpha J of Rn, this means it's a line that does not intersect this affine hyperplane. So that means it's a line that's entirely contained in this subvector space, right? Okay, then L is contained in the orthogonal complement of Ej entirely for all J. And the intersection of these orthogonal complements is just the origin. So L is not a line, and that's a contradiction. Okay, so that proves the claim, and that's in particular proves also the first statement assumption here. All right, good. And now, second condition. I'm doing this in a bit of detail so that we see, at least in one example, how this theorem is applied. So if we take the intersection of any two such sets, now we are back to general embeddings. And so what is the intersection of two such sets? So what's missing here? Here we are missing all those lines that are contained in the linear space corresponding to the affine space alpha of Rn. And here we are missing all those which are contained in the linear subspace corresponding to the affine space beta of Rn. Okay, so we have, okay, here's the origin, so this is alpha of Rn, and we have some, and so if we are intersecting with this, I could also write this as U alpha, and I remove everything which is not contained in here. And these, the ones which are not contained in here, are the lines which are contained in a certain vector subspace of codimension 1. So let's say, how should I draw this? So this is alpha of Rn, that's the origin, and beta of Rn is a parallel translate of this. This is a vector subspace. So this is the image of the linear part of the affine map, corresponding to the embedding beta. Okay, and these ones, the lines that are in here, are removed. They are taken out of this. And so what does this mean? So if we look at the intersection of this vector subspace and this affine linear subspace, then these such two affine subspaces always intersect in an affine subspace if they intersect at all. So what we really get is we get all lines which hit alpha of Rn except for some affine subspace. So this is, so if we take apply then x alpha to it, then here this alpha of Rn is mapped to Rn projectively, and then we have an affine subspace, which is mapped to an affine subspace of Rn plus 1. Affine subspace. So what we have here, this intersection is mapped to the complement of this affine subspace. An affine subspace is always a closed subset, so the complement is an open subset. And this proves statement 2. So this is equal to Rn minus an affine subspace. We don't even have to know the dimension, and therefore it's therefore open. because an affine subspace is closed. Okay, so that's condition 2. And finally we have to show condition 3, which tells me that these transitions from one chart into another are actually that they are homeomorphisms, right? These things must be homeomorphisms. And so what time is it? 10 minutes past 3. So third condition. So let's compute this transition for two such affine spaces. So x beta composed with x alpha to the minus 1. And maybe I write them down explicitly. So I write alpha of v should be given as b times v plus c. And the b is the matrix, c is the translation vector. And similarly for the other one, let me call this matrix to be in agreement with my notes as d v plus f. And so these are these matrices as here, and these are translation vectors in Rn plus 1 as this one. And they are non-zero, so in particular non-zero, so they do not lie in the image of these matrices respectively, because otherwise 0 would be contained in the image of the space. Anyway, so let's compute this this transition map. So compute it. So let's do that. Okay, how do we do it? So x beta composed with x alpha to the minus 1 applied to some vector v is equal to some vector w if and only if what's true. Well, we have bring this bijective map to the other side. X beta to the minus 1 applied to w is equal to x alpha to the minus 1 v. And the inverses of these maps were more easily written down. So this is equivalent to saying that apply beta to w and then take the line, and that's equal to alpha of v and then take the line. This is this formula for the inverse. And so that means this vector is a multiple of that vector. This is TR such that b of w equals t times alpha of v. All right, and now I can insert these formulas for the maps. So that's equivalent to having such a t such that d w plus f is equal to t times b v plus c. All right. Okay. And this I can also write in a little bit more fancy way by writing it as a matrix D, comma 1 applied to the vector W F. D F applied to the vector W1. Right, this is an n cross n plus 1 matrix. I add another column, so I get an n plus 1 cross n plus 1 matrix applied to an n plus 1 vector. And okay, and since this is not, this vector f is not in the image of D, this n plus 1 cross n plus 1 matrix is actually invertible. This is in fact this condition here. So this n plus 1 cross n plus 1 matrix here is invertible. Okay, and let me now determine this value of t so that I can plug it back in. How do we get to this value of t? Well, we could take this matrix, take its inverse, put everything on the left side. So that means we have W1 is equal to T times df to the minus 1 applied to B plus C. And now here the lowest entry in this vector is 1. So let me just take, so this implies that if I take the scalar product with the last vector, n plus 1, this is the same as the right hand side. Scalar product with this, oh no, it's En. As you reminded me, there is no En plus 1. That's the last vector here. E0 up to En. So I have this expression here. Scalar multiplied with En. And of course, this scalar product is equal to 1. Now this is the vector 0, 0, 0, 1. So now I can solve for t. Namely, we get 1 on this expression. So it's this expression here to the minus 1. And now I can insert this back into this formula. This won't be needed anymore. So that means we have I want to insert it back in here. So what we have is W1 is equal to T, so where's the formula? This formula. Here I want to insert it in here. So T times df minus 1 EB plus C, and here we have 1 on this scalar product here. That's what we have. And we want to, well, what we want to do is we want to find a formula for this map. So we want to see how W depends on V. So now if we look at this, we see, well, we have expressed W in terms of V. And where is V? V is here and here in the formula. Now in this, so everything else is fixed, right? D, F, B, and C are fixed matrices in vectors. And V is the argument. And so what we see, this expression here is affine linear in V. This expression in the denominator is also affine linear in V. So if you look at any component of W, you see it's a linear, it's a quotient of certain linear, affine linear map, a function of V divided by an affine linear function. So it's a rational function. So therefore, x beta composed with x half to the minus 1 is a rational function. Hence, continuous particular. And this is what we needed here. Actually, it would be sufficient to write continuous because we know already that these maps are bijective. And so if they are continuous in both directions because we can interchange the roles of alpha and beta. So it's sufficient to write continuous here. And this is a rational function, in particular continuous function. Okay, anyway. So if we apply the theorem in this example, we see that this RPN carries a unique topology, which makes it locally homomorphic to Rn. Now that's what the theorem says. Maybe I should also say a little bit about the theorem itself. So may I erase this left part already? Is it okay? So a little bit about the proof. It says that there's a unique such topology, uniqueness. Let's check uniqueness. It's often good to start with uniqueness because then one often gets a formula for it, which one can then use as an ansatz for the existence part. So let's see. All right, uniqueness. So suppose we have such a topology. Suppose M has such a topology. We want to show that it's unique. So let's see if we can characterize it in terms of these U alphas, X alphas, etc. So U in M open, then from this we can conclude then the U alpha are also open. So intersection of two open sets is open. So then U intersect U alpha is open for all alpha. Okay. And since these X alphas are homeomorphisms, we can apply this and we see that X alpha of U intersect U alpha in Rn is open for all alpha. So that's what we have, certainly. And now one has to check that this condition here actually defines a topology. In fact, so if these are open for all alpha, then since these are homeomorphisms, then these are open for all alpha. But if these are open for all alpha, we can also go back here, because if we take the union of all alphas, then we get U. This uses this first statement. So we have these equivalences. And you see, this is a characterization now entirely in terms of the U alphas and the X alphas. So we have somehow written down a formula for the topology, if you like. So that's the uniqueness part. And the existence part is then simply take this as a definition, take this condition star as a definition, for openness, and then check that this defines a topology. And you have also then to check that the rest of the conditions. That this defines a topology and that U alphas are open and these are homeomorphisms. So in particular, that these are continuous. We know it's bijective, so continuity in both directions has to be checked. This is pretty straightforward, it takes a little bit of time. I'm not doing it in the Moodle defined lecture notes on differential geometry, where this is carried out in detail if you really want to see. But it's pretty straightforward, so you could easily do it yourself. Right, so I don't want to spend more time on this. All right. Questions so far? So that's, of course, only taking care of one of the conditions of manifolds, namely that it's locally homeomorphic to Rn, but there are also these two other conditions, like Hausdorff and countable basis. And if we start with such an approach, for example, in this example of RPN, how can we see that the other two conditions are also satisfied, so that this topology that we have just defined really gives us a manifold? So there's addendum 1 to the theorem, which takes care of the countable basis. So if we are in this situation, assumptions as in the theorem, but we refine this first statement by saying that already countably many of the alphas, of the U alphas, are sufficient to cover all of M. So assumptions as in the theorem, and there exists a countable subset A prime in A, such that the U alphas that are contained in U prime already cover M. Then the topology constructed in the theorem, topology of M, has a countable basis. And the proof is simple. So each U alpha is homeomorphic to V alpha via the corresponding map X alpha, and that's an open subset of Rn, and Rn has a countable basis. So in particular, V alpha has a countable basis. Therefore, U alpha has a countable basis. B alpha. And now the union of these countable sets B alpha over the countable set A prime is again countable. Let's call this B. This is then a countable basis for the topology of M. This is a countable basis of M. That's the proof. And we can easily apply this in the example, because I have already shown you earlier that in this case we can actually do with finitely many U alphas. We have seen that A prime consisting, in the example, A prime consisting of alpha 0 all the way up to alpha n. So this already does the job, so even finitely many. So the topology we have constructed in RPN does have a countable basis. That's the first addendum. And the second addendum needs to take care of the Hausdorff property. So assumptions as in the theorem. And now, in addition, we assume for any P and Q in M, so and assume for any P and Q in M, there exists one chart which contains them both. So there exists an alpha in A such that P and Q are both contained in U alpha. If this is the case, then the topology is Hausdorff. Then the topology of M is Hausdorff. And why is this? Well, the proof is simple. Proof. If you have these 2 points, so let P and Q in M be 2 different points, then we choose such an U alpha. Let alpha in A be such that the corresponding set U alpha contains both of them. Now again, this is homeomorphic to V alpha in Rn. So we have, so here's P and Q, U alpha. We map them via X alpha to V alpha. This goes to points here, but here we are in Rn, and Rn is Hausdorff, so we can choose small balls containing these points which are disjoint. So that means there exist V and V prime in V alpha open, such that P is in V and Q is in V prime, and they are disjoint. And then, of course, we just take the pre-images under X alpha and we get the corresponding separating open neighborhoods in U alpha. Then X alpha to the minus 1 of V contains, that's actually X alpha of P, right? X alpha of Q, these 2 points. X alpha of P, X alpha of Q. And this now contains P, X alpha to the minus 1 of V prime contains Q, and of course they are disjoint. So this way we can translate things back from Rn. Okay, so that's the proof of this addendum, and let's see how this applies in the case of projective space. Okay, so we have 2 different lines. Let L and L prime be 2 lines, so 2 elements of RPN, different ones. Well, then we can certainly actually for the assumption here, I don't need to make the assumption that it's different. If they're equal, it's trivial, right? So I just want to check addendum here, and here I don't have to make the assumption that they are unequal. So we have 2 lines, L, L prime. So we just have to, let's take a vector here, and let's take a vector here, and then we just take a affine hyperplane containing these points. And then there exists certainly an affine linear embedding alpha in Rn to Rn plus 1, such that they all contain these points so that they intersect, such that L intersects the image, L prime intersects it too. And then this means that these 2 points of RPN, L and L prime, are both contained in the corresponding chart U alpha. Therefore, L and L prime are contained in U alpha, and that's what we need to check. Okay, so the upshot is with the theorem, the 2 addenda, we see in particular that RPN carries a unique topology which turns it into a n-dimensional manifold in such a way that these affine linear embeddings lead to charts. You could do the same thing with complex projective space. Then the only difference would be that you have Cn here and Cn plus 1 here, and you would look at complex lines, but everything else would be the same. You identify then Cn with R2n and Cn plus 1 with R2n plus 2, and you see that complex projective space would so similarly. So complex projective space, that's the one I mentioned in the introduction, which corresponds to complex lines, L in Cn plus 1. So that would be a complex one-dimensional subspace, subvector space. So this, then I would get charts which taking their values in Cn, which is R2n. So it's a 2n dimensional topological manifold. Exactly, but the construction is exactly the same. We're just doing everything over the complex numbers. All right. Good questions so far. That's all basically I wanted to say about topological manifolds, or to remind you, because we will also use this theorem later for different types. Well, that's a way to topologize spaces and turn them into manifolds. As I said, you can find all details and a more detailed discussion of this in the lecture notes on differential geometry, which you find in the Moodle of our course, if you want to look up things. Questions? Everything is clear. Totally clear. That's good. Now, we do differential geometry, so we have to differentiate at some point. And that's not really possible on topological manifolds. So, why not? What would be it? So we know what continuous functions are on the topological space, in particular on a topological manifold. We do not know what differentiable functions are on a topological space. It makes no sense. In the case of a manifold, we could say, well, a function on the manifold is differentiable if, when composed with a chart, it gives me a differentiable map on Rn. That would be natural definition. But then, if you change the chart, you have to compose with the chart transformation map, and this is in general only a homeomorphism. So if something is differentiable in one chart, it may be non-differentiable in another chart, and that's not good. Right, that's bad. Because differentiability should not depend on the choice of coordinate system we are using. And for this reason, people have just defined away the problem by making the following definition. Two charts, x and y, so let's say x from u to v and y from u prime to v prime of a topological manifold are called C infinity compatible. If the problem doesn't occur. Meaning, if the transition of, so we go x composed with, y composed with x to the minus 1, which goes from v to v prime. So that's a homeomorphism of these two open subsets of Rn. And since this is in Rn, it makes sense to talk about differentiability. And so if this is a C infinity diffeomorphism. So if this, then if I have two charts which are C infinity compatible in this way, and I have a function on the manifold which in chart X is differentiable, it will also be differentiable if I express it in chart Y, because I just have to compose with this, which doesn't destroy differentiability anymore. That's the reason why one makes this definition. And now, definition, a collection of charts, let's say a collection A of charts of a topological manifold is called M. It's called an atlas of M. If the corresponding charts, let's say this is a collection of x alphas from u alpha to b alpha, with the corresponding chart domains, so cover all of A. So I have a collection of charts. If I cover everything, they form an atlas. Yeah, that's right. That's true. I have to restrict to the intersection. So what I have to do is, okay, we start here. We have to take x of u intersect u prime to y u intersect u prime. Right? More like that. Yes, that's true. I can form this composition only where it's defined. And these are open subsets of V and V prime. All right. So that's a collection of charts is called an atlas if the charts cover the whole thing, the whole world. And if I have such an atlas such that any two charts are C infinity compatible, then I call it C infinity atlas. So A is called C infinity atlas if any two charts in A are C infinity compatible. Okay, compatible. And if I work with such an atlas, then I have no problem in defining what a smooth function is on my manifold. Because I would just say a function is smooth if, when composed with any of the charts in this atlas, it is a smooth function on Rn, or a subset of Rn. And passing from one atlas chart to another does not destroy this property because of this compatibility. So that's the reason why people invented this concept of C infinity compatible charts and atlases. And now, last remark really I want to make for today is this. Let A be a C infinity atlas. Then how would I want to formulate it? Yeah, and if x and x tilde are charts not contained in the C infinity atlas, any charts of the manifold. If they are charts which are C infinity compatible with all charts in the atlas, with all charts in A, then they're also C infinity compatible with each other. Then x and x tilde are C infinity compatible with each other. It's not as trivial as it might look. You have to think a little bit about it. It's not difficult, but not completely trivial. And in fact, on the current exercise sheet, number 1, which you find today in the Moodle system, there is an exercise related to this. So you can think a little bit about it. But the consequence of this is, if I start with the C infinity atlas, then I can add all charts that are compatible to the charts in A. Then they will also be compatible amongst each other, and so I will still have a C infinity atlas. So A max, which is defined as the set of all charts X, for which X is C infinity compatible with all charts in A. So I add all charts which are compatible with all the charts that I have already in A, and that's the definition. Then this is also a C-infinity atlas. And the max stands for maxima, because now there are no charts that you can add and make it even larger, because we have already added all charts which are compatible with A. If you add anything that would, anything further that is compatible with all charts in here, it's in particular compatible with all charts in A, and so it's already in there. So that's, you cannot increase this atlas anymore. So that's a maximal atlas, C-infinity atlas. And such a thing is called a maximal C-infinity atlas, or also a differentiable structure on the manifold. Definition. A maximal atlas, C-infinity atlas, is called a differentiable structure. On the manifold. And this remark tells us that each C-infinity atlas is contained in exactly one maximal atlas, exactly one differentiable structure. So remark, each C-infinity atlas is contained in a differentiable structure. And a differentiable manifold is now just a pair of a topological manifold equipped with a differentiable structure. That is the definition for that. A differentiable manifold is a pair M, A max, where M is a topological manifold and A max is a differentiable structure. Now there are some famous classical questions about this. For example, does every manifold, topological manifold, have a differentiable structure? Is it always possible to find, if I find any C-infinity atlas, then yes, right? If I find a C-infinity atlas, then there is a difference, because then I can just pass to the maximal atlas and have a differentiable structure. But maybe there are topological manifolds which do not have any C-infinity atlas. What would you think? Is this possible? It is possible. So there are such examples. It may happen that a topological manifold does not have. It doesn't happen in dimension 2 or 3, but it does happen in dimension 4, for example. And yeah, and then there are other questions like maybe there are essentially inequivalent differentiable structures on one topological manifold. So meaning maybe I can take a topological manifold, put two different differentiable structures on it, and such that these are no longer diffeomorphic, so that I cannot find a diffeomorphism between these two differentiable manifolds. And the question is, can this happen? And yes, it can happen. Again, it does not happen in dimension 2 or 3, but it happens in dimension 4 and higher. And even on Rn it can happen. On Rn, the following is true. There are inequivalent differentiable structures on Rn itself, only in dimension 4. It does not happen in low dimensions, 2 or 3 or 1. It also does not happen in high dimensions, 5 or higher, but in dimension 4 there are. So that's quite remarkable, and it was in the 1980s or so that these things were discovered, and I was just starting my studies at the time, and I still remember the excitement of people talking about that at the time. Yeah. Anyway, so that's, okay, I'm already over time, I'm very sorry for that. So this is what I wanted to say about manifolds. One remark, I said that we will also use the computer algebra system, Sage Math, to do computations of examples. I will not do this in the lecture course. I will provide you with a few videos as an introduction, and the tutorial class this week, where we do not yet have any exercises to discuss, will be devoted to this. So if you go to the exercise class taught by Rubens on Thursday morning, very early morning, 8 something, early morning, then you can discuss, say, I hope to be finished with the videos by tomorrow. I can't really promise, but I do my best. And then you will find them in the Moodle also, right? And then you can look at them and see if you see how this works. And if you have never used Sage before, you should maybe go to its web page and take a look how basic functionality works. It's not difficult to get into it. And there's this wonderful differential geometry functionality, and it really works like in mathematics, like I explained it here. So you declare a manifold, you declare charts, you tell the system how the charts are related to one another, etc. And then you can come up with all the structure, vector fields, differential forms, tensor fields, connections, everything we will need in order to curvature, in order to do characteristic classes. But the nice thing is all these computations, which can be tedious if you do them by hand, are just done by the computer in a millisecond. So I really recommend to take a look at Sage if you don't know it yet, and then look at the differential geometry part of it, which I provide the videos for. Unfortunately, there are no good videos at the moment, so I have to do it myself, unfortunately, but I hope to be done by tomorrow. You will find it in the Moodle system. It's a very good tool to have anyway. Okay, so that's it for today. I thank you for your attention, and sorry again for going over time.